In this video, we'll look at solutions. Solutions are defined as a homogeneous mixture of two or more pure substances. The solvent is present in the greatest abundance. That is, whatever molecule has the greatest number or largest number of moles present is known as the solvent. Anything else present in the solution is known as the solute. So we always dissolve solutes into solvents. When we place an ionic compound into a solvent, it undergoes the process of dissociation. That is, the ions break apart into cation and anion and are surrounded by the solvent. So in solutions, you can have ions transversing around the solution, whereas in solid and gas phase, this isn't normally possible. When you have an ionic compound dissolved in solution, you have an electrolyte solution. An electrolyte solution is a solution that simply contains ions, often described as being dissolved in water, although not exclusively. A non-electrolyte solution is a solution that does not contain ions, but does have some other molecule dissolved in it. So molecules, that is, compound or materials containing nonmetals bonded to nonmetals, form non-electrolyte solutions because the molecules are there. They're just not sticking to each other like they would in a solid. When it comes to describing electrolyte solutions, however, we have a couple of different descriptions. We have a strong electrolyte solution and a weak electrolyte solution. A strong electrolyte solution is when the ionic compound completely dissociates 100%. So that there's no remaining compound left together, it's all ions. If we talk about conducting electricity in a strong electrolyte solution, then what we find is that as you increase the electrolyte, the intensity or the conductivity of the solution increases. A weak electrolyte, on the other hand, only partially dissociates. That is, there is a small number of ions that actually go into solution, but everything else pretty much remains the same or remains together as a solid. So it would typically look like most of your solid goes straight to the bottom of the beaker with just a small amount of it actually dissolving. Unlike a strong electrolyte, if you add more of a weak electrolyte to a solution, the conductivity really doesn't change at all. So what do we consider electrolyte and non-electrolyte materials? Well, electrolytes are anything that are ionic. Strong electrolyte solutions can be made of strong acids or strong bases, as well as any ionic material that contains a positive 1 with a negative 1 charge. So column 1 and column 7 elements both form strong electrolyte solutions when they're paired up with each other. The higher the ionic charge, the less likely it's going to be able to dissociate. And so weak materials, weak acids, weak bases, or highly charged ionic materials make weak electrolyte solutions because it becomes increasingly more difficult to separate highly charged particles from each other. Non-electrolytes are simply molecules, that is, nonmetals bonded to nonmetals, and there are no ionic materials that form non-electrolyte solutions. So molecular compounds tend to be non-electrolytes except for acids and bases. So we talk about acids and bases as being electrolytes. So what is an acid? Well, according to a chemist by the name of Arrhenius, an acid is any molecule that increases the hydrogen ion concentration when dissolved in water. This definition was later expanded by two scientists by the name of Bronsted and Laurie to define them as basically any molecule that donates a proton or puts a hydrogen ion into solution. When it comes time to describing acids, there are only 7 acids which are strong. All other acids will be weak. So if you can identify an acid from its formula, and you should, because acids always start with a hydrogen, and then they also have aqueous as their phase, then the 7 strong acids are hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric acid. If it's not one of those 7 acids, then it's weak. Bases are conjugates of acids, or the opposite of acid. Whereas an acid donates a H plus into solution, according to Arrhenius, any molecule that increases the hydroxide concentration, or the OH ion, is considered a base. Bronsted and Laurie redefined the definition of a base as any molecule that can accept a proton because ammonia, NH3, is known to be a base, but there is no hydroxide present in it. So the definition had to be rewritten a little bit because of the ammonia molecule. When it comes time to describing strong bases, the alkali metals, that is column 1 metals with a hydroxide, calcium, strontium, and barium all form strong bases. Otherwise, anything with a hydroxide is going to be considered a weak base, or a weak electrolyte. When we try and communicate how much material is dissolved in a solution, we use what's known as molarity. Molarity is simply how many moles of a solution, or how many moles of a solute you have dissolved in a solution. So molarity is represented with capital M, and it is important that you use a capital M when communicating molarity, as a lowercase m means something completely different. So you have to be careful there. Molarity is simply moles of solute divided by liters of solution. So it's always moles per 1 liter. When we make solutions, we create our solution by weighing out some substance so we can measure how many grams it is. And then we can use that mass and put it into a graduated cylinder or a beaker and fill it up with some volume of water to get a certain molar concentration solution. So the process can be a little tedious if you're going for an exact molarity, but it doesn't take that long. So when you make a solution, we tend to make highly concentrated solutions, or what we call stock solutions, solutions with high molarities. And by high molarities, generally if you get a 10 molar solution of anything, that's pretty concentrated. So molarity doesn't go up past 10 too often. But when we make a stock solution, we're often making it so we don't have to make a solution every time, go over to the scale, weigh it out, go back, dilute it. What we want to do is just be able to pour a little bit of our stock solution and dilute it to an ideal working concentration. So taking something that's very concentrated and making it less. And the way we can do that is by taking the molarity of our stock solution, so we'll say that's the molarity of molecule C, and multiplying it by some volume we desire in liters, and then that's going to equal our new molarity times our diluted volume. So we say M1V1 equals M2V2, or MCVC equals MDVD. And what this equation does is it just communicates how many moles you have of something in solution divided by the overall volume of solution which it occupies. So what's important here is to realize the moles of material in a solution does not change during the process of dilution, only the volume in which they occupy. So if you had 1 mole of a solution and you go to dilute it, you're still going to have 1 mole. It's just going to occupy a bigger volume. We only use this when we're calculating dilutions. Some instructors and YouTube videos will say that you can use this all the time. You can't. You can only use this equation when you're doing a dilution. So there are other ways of representing how much material you have dissolved in solutions. We have parts per million, which is simply the mass of something divided by the total mass present. And because it's a relatively small amount of material there, it's multiplied by 10 to the 6. We can also have parts per billion, which is calculated the same thing, except instead of multiplying by 10 to the 6, we multiply by 10 to the 9th. We can represent something by mole fractions. That is, moles of some component divided by the total moles present. Not used very often in chemistry, although we will see it a little bit. We've got molarity, which we've described, and we've got molality, which is moles per kilogram, and this is represented with the lowercase m. So again, you want to make sure you're paying attention to whether you're dealing with capital M or lowercase m. Most chemistry classes we deal with capital M, moles per liter.